Good morning, everyone. It is my pleasure to introduce today's speaker, Robert Hoindorp, who is an associate professor of computer science at the King Abdullah University of Science and Technology in Saudi Arabia. Robert over there leads the biontology research group, which focuses its investigations on the use of ontologies for data integration, as well as analysis in the domain of biology. Now, Robert's work has been around the development of ontologies, as well as the application of these for data integration and annotation, as well as for building ontology-based machine learning models. Now, some of the applications of this work are in understanding sort of the molecular basis of human diseases, as well as personalizing medical diagnosis and treatments, and the prediction of functions and phenotypes. So in today's talk, Robert will speak to us about machine learning with ontologies, and perhaps also give us a glimpse into the world of ontology-based semantic similarity. So with that, thank you so much, Robert, and take it away.
Thank you very much for the kind introduction and for the invitation to speak here. So I'll talk not so much about semantic similarity, but more about machine learning with ontologies. But I will start a little bit with semantic similarity just because it makes a very nice story in terms of how methods have developed. But before I do that, let me talk a little bit about where all these methods that I'm going to talk about come from. And they come from formal logics as a foundation of artificial intelligence. So in general, in AI, if we build an intelligent agent, we want our knowledge of the world to affect our decisions. So we want to perform, or want our agent to perform an action if we believe, or if our agent believes that the world satisfies a proposition P. For this, we need to have a way to represent this knowledge of the world. And for this, we use symbols. So we use symbols, which are entities which denote, so they stand for something else, and we can interpret them, so we can understand what they stand for, and we can combine them into symbol structures to form more complex expressions. And these systems, so symbol systems, physical symbol systems, have been the foundation of artificial intelligence for over 50 years. And this is the famous physical symbol system hypothesis from the Turing Award lecture by Newell and Simon a very long time ago, where they stated that a physical symbol system has both the necessary and sufficient means for general intelligent action. That means as intelligent as a human. And the crucial idea here is that this proposition P may not be, that we want to test whether the world satisfies it, may not be explicitly represented, but it may have to be inferred using some form of reasoning or deduction. So I'll touch a little bit on this today, but the main methods for implementing this, or for implementing physical symbol systems now, are mathematical logic or other formal systems. And ontologies, especially in biomedicine, are a way, are based on this formalism. So ontologies, ontology is a discipline which comes from philosophy, where it studies the nature of existence and categories of being. But in computer science, ontology has a very specific meaning, at least since Gruber in 1993, where it's an explicit specification of a conceptualization of a domain. But from a practical point of view, what does that actually mean? So I put down here a small part of the plant ontology. So the plant ontology, PO, is an ontology which is in the OBO Foundry. So it's a community ontology to characterize plants. You can see in this small part of this plant ontology several features that ontologies provide. So first, they provide identifiers for classes. So for plant structure, for the gynoecium, for the ovary septum, and so on. And these identifiers can be used across different databases in order to integrate data from different databases, because they may use the same identifiers. The second feature is that there are labels. So you see that each of these classes has a label. They also have some additional information, so synonyms and definitions, which allow humans to understand this. So the labels may provide a vocabulary. So if you need a vocabulary of plant structures, you get this from the labels of this ontology. And if you want to understand as a human what each of these classes refers to, then you can read the definition, and each of these classes has a definition. But there's a fourth feature, and this is these arrows here. And these arrows, there are two types of arrows. So the one here, this white arrow, this is a subclass arrow, and it stands for an axiom. So it constrains formally using a logic-based language. It characterizes some form of the meaning using this logic-based language so that machines can understand some aspect of what it means to be, for example, an ovary septum. So an ovary septum is a septum. So it's a subclass of a septum. There's another type of axiom here, which is a part of axiom. So here, every ovary septum is a part of some gynoecium. So this is what this axiom, represented here just as this edge, expresses. And you can see this whole definition here, which comes from an ontology called the oboe relation ontology, which characterizes using a logic the meaning of these kind of arrows in the oboe ontologies. Now, we use symbolic methods because they have been very well studied for over 2000 years. So many of them go back to Aristotle and Greek philosophers. And we have a lot of investigation into the theory. So in model theory and proof theory of these methods, where we have formal guarantees that these methods can provide in terms of soundness or completeness of the answers. So we have algorithms and we have these formal guarantees. And they are also inherently interpretable and therefore explainable because they rely on symbols which are accessible to us as humans. So we, in order for a symbol to be a symbol, we must be able to understand what it stands for. And there's one more, so this makes biases maybe explicit. It doesn't remove the biases, but it can make them explicit. And there's one more feature. We can also use this deductive inference for a form of prediction, which I call a zero-shot prediction or maybe zero-shot learning, where we can use this deductive inference to make predictions without training data. And I'll show you in the end of this talk today how to do zero-shot function prediction or zero-shot prediction of phenotypes using these methods. So the question that I would like to address today is whether we can incorporate some of these properties of symbolic methods in modern machine learning models. So the question is, how can we combine this? And this is a very broad figure where we have a symbol systems or some kind of knowledge representation language together with some reasoning system on the left-hand side. And we would usually, as humans, we communicate in symbols. So this is something that gives us answers that we can understand. So we can read from the system and we can write to the system, so we can add new information to such a symbol system because it's opaque. So it's something that we as humans, it corresponds to how humans communicate. And we can perform some form of reasoning. So we can reason over this. We can test, for example, consistencies or are there contradictions in the statements that the symbol system that are represented. And on the other hand, and this is where our ontologies are, but we also find other systems here on the left-hand side. We find also knowledge graphs and knowledge bases. So a lot of the symbolic representations. And the right-hand side, you basically see things that I just call this data. It's a little bit imprecise, but it's things that we measure, and it's usually unstructured or very loosely structured, but it's things that we observe, especially in a bioinformatics context. We will read or we will observe large amounts of sequences or just reads or short reads or gene expression data, big matrices full of values or metabolomics profiles. And in these, on this side, on this data side, our task is usually to identify or recognize patterns which somehow characterize this data. I call this here learning, but it's essentially a form of pattern recognition. And you would see that the data is usually what we measure, and on this symbol side on the left, it's what we want to infer. So we want to understand what is the relationship between a genotype and a phenotype, or how does a protein based on its sequence relate to its function? How does gene expression correspond to a disease state? So on the left-hand side is the information that we want to gain, and on the right-hand side is what we can observe from the world. And there are these two arrows in the middle, and I will mainly talk about one, but a little bit also touch on the second one. So the first I call the embedding arrow, where we take a symbolic representation and embed it into the data space so that we can use it as background information or background knowledge to recognize these patterns. Then, after we recognize patterns, perform machine learning here, we would extract again a symbolic statement, a proposition, something that is true or false, and incorporate it in our symbol system so that we can compare and relate it to what other facts we know to be true, and for example, test whether our prediction or this pattern that we have recognized is consistent with what we know to be true about the domain in which we operate. And of course, this goes into a big cycle so that we can iterate this as a single system. So I will mainly talk about the embedding part. And because it makes a very nice narrative, I will start with something that is a rather old technique, which is semantic similarity. And I will show you how it relates to embedding of knowledge. So in general, we want to use the knowledge in our ontologies to determine in semantic similarity. We want to use the knowledge in our ontologies, or maybe also in graphs. So I'm in knowledge graphs or other graph-based representations. We want to use this to determine some similarity between either classes or instances of classes, or some things, entities, which are annotated to these classes. So you can think of this as a gene with its functions, or you can think of a patient with its phenotypes, or maybe a mouse model or an animal model with the phenotypes that have been observed. And we do this usually in order to determine some form of relation between these entities, which we believe to be true if they are quite similar. So I give some examples of questions that we can answer with semantic similarity measures, because they are very similar to the questions that we are going to answer with embeddings. So one question, for example, is whether cyclin-dependent kinases are functionally more similar to lipid kinases or to riboflavin kinases. And we can also ask this question, what about, first about function? We would use gene ontology annotations for this. And we can also ask this question whether they are phenotypically more similar, where we think of knockouts. It may be in an animal model, a knockout, or it might be a loss of function variant in a human, and we see some rare disease. We want to test whether this is, which of these is true, which of them are they more closely related to. Or we can ask which protein in the mouse is functionally most similar to some zebrafish protein. This allows us to ask questions about evolutionary biology, for example. Or we can ask which mouse knockout resembles Bardet-Biedl syndrome 8. So this is a very specific syndrome. We can get the phenotypes from OMIM or from the HPO database. Well, and if we can find a mouse which looks very similar, well, then maybe we have just identified a gene or the ortholog of a human gene, which causes something that resembles Bardet-Biedl syndrome. We can ask similar questions about drug effects. So we can ask, for example, whether there are mouse knockouts that resemble the side effects of diclofenac. We can use this to test whether, to find targets of diclofenac or this drug. We can look, we can apply this to infectious disease and so on. So the applications are limitless. So we can ask which genetic disease produces similar symptoms to COVID-19. It might allow us to hypothesize that the pathogen targets a particular protein in the human, and so on. So we can ask many of these questions just using semantic similarity. And I will show you one method only. So this is from a small ontology called Pato. It's just an ontology. I like to use it because it's very clear. We don't have to know much biology or biomedicine for this. It's just about colors and shapes and general properties of things, this Pato ontology. But you can find this ontology. It's in wide use in many phenotype ontologies or settings. So we want to understand similarity between two classes. And one of the simplest measures is simply to define it based on the shortest path in such a graph, which is just based on this subclass or is a type axioms. And then we can define this. So we can define the distance on this shortest path between two classes. And then we say, okay, the similarity is 1 divided by the distance plus 1. So we don't divide by 0. So when you look at this, the distance between red and green is 1/3, just because the distance or the similarity between red and green in this ontology is 1/3, just because the distance is 2 in between them. Now, I could talk for hours about semantic similarity measures. I'm not going to do this. So this is just a small introduction, because the reason I can't do this is that there are literally hundreds of semantic similarity measures. There are very, very many of these. So there is no obvious choice, and it may not be a very fruitful area of research at this point, because most of this has already been explored. So you can, when I show you this graph, you can very easily say, oh, maybe shortest path is not so useful in some cases. So you will already, just by thinking about this problem, come up. If there are 10 people in this room, then you will probably come up with 11 different new similarity measures. So we are not going to do this. There are, however, some things that they are limited by. The first one is that they ignore most of the axioms in ontologies. So part of, but more importantly, things like disjointness. So two classes are disjoint. They cannot be the same. They cannot have instances which are shared. It's something that they cannot deal with easily. Most of them are just doing these taxonomies. They ignore labels and descriptors. So a more fruitful question may be to ask whether we can find some way to determine this relatedness in a more data-driven way. Maybe something that is dependent on the problem that we try to solve. And this is where we start going into embeddings. So an embedding, and I do like to define embedding. I know that many of you may be familiar with the notion of what an embedding is, especially if you work on machine learning, but I do like to define this formally, what I mean by embedding, because it's not commonly done and it makes some things very explicit. So an embedding is a structure preserving map between two mathematical structures, such x and y, such that the first structure x is preserved in y. So we have to make three things explicit when we talk about an embedding. The first is, what is this mathematical structure x? What is the mathematical structure y? And under what operations is x preserved in y? So these are three questions we have to answer when we define an embedding. But the main reason why we define an embedding is that maybe the second structure, y, is just more suitable for some things that we want to do than x. So you have seen these symbolic representations. It's possible, but not so straightforward to define some similarity measure on them. So maybe we find a structure in which there are more natural ways to define similarity. And maybe the structure allows us to do other things as well. For example, to compute gradients and perform some optimization by gradient descent. So we normally would want to embed a knowledge base as our first structure in the Rn, mainly because the Rn is what we use when we use neural networks or similar gradient descent based optimization algorithms. And the question is, which part, or what is our first structure x, and how are we going to preserve it within the Rn? So we would like to have neural networks that can access the knowledge in our knowledge base that we started with. We have in general three approaches for this: graph-based, syntactic, and model theoretic approaches. I'll just briefly talk about the first two and then a little bit more elaborately about the third one, because the third one has some very interesting properties that allows it to be used quite flexibly in many different scenarios, which we did not initially expect. So first, let's talk about this, the first one. So if we can generate a graph from our ontology, I have shown you some graphs already. So each of these edges is now an axiom. We can also call this a knowledge graph. If we do this, it's not so straightforward to generate this. For example, this dotted line here is a line which you would not easily find. You would have to deductively infer it. So you would have to because FOXP2, this is a protein, it's involved in language, in human language. It has this function, which is vocalization behavior here, which is a subclass of behavior. And from these axioms, we can infer that FOXP2 also has this function of behavior. This is in the context of Go, it's called a true path rule. But we can also do this using our logic formalisms, or many ways in which we can encode this. But I just put this here so that we can or cannot include this. And then there are many ways in which we can embed such a graph. So we could, for example, do this based on some random walks. There are other methods like translational based methods that can do this maybe better than just based on random walks. We can have biased random walks like in Notebag with or without including these edge labels. So there are many different ways in which we can do this. And then we get an embedding in the Rn. And this is maybe not so surprising for you, and these embeddings, so these are vectors for each of these entities and for each of the relation. We can then use this, for example, to compute similarity or to predict some edges. So we did this 2017. It was one of the earliest papers which used this in biology. And so we did this, and it was very nice. It was published in Bioinformatics, and you could see that this was without the deductive closure, and with this deductive closure, we separated this. And in 2017, what my hope was, because my background is in logic, well, if we compute this deductive closure, so with reasoning here, we would get a much better performance. Obviously, we have access to a lot more information than if we do not use this deductive closure. And as you can see, this my hope was disappointed. So I was very disappointed when I saw these results. Essentially, there is no difference, and maybe sometimes a little bit better, sometimes a little bit worse, literally no difference, with or without closure. And of course, you will immediately say, well, you used a pretty stupid approach, just using some random walks there. That can't possibly work, especially you're going to have this very, very dense graph if you just add this deductive closure, these inferred edges in there, so it's just not going to. Well, we tried something else in between, so I call this a graph-based approach. We have other graph-based approaches. Now, so when you look at some of these axioms, so these are the axioms in gene ontology, you don't get these axioms in a graph. So it's just very, very difficult to put these axioms, to put them in a graph in the first place. So this is like behavior is something that only occurs in metazoa. Behavior and developmental processes are disjoint. Cell proliferation and things which occur in fungi are disjoint, which means cell proliferation is not something that occurs in fungi. Cell growth is equivalent to a growth which results in the growth of a cell. So these are axioms which you can find in Go. So if you take gene ontology and you take the OWL file and open it in Broadachet, you'll see these axioms. And we asked the question, well, what about this? Can we maybe embed these axioms directly, just using a language model? This is language, I can read them and it sounds like language, right? So can we do this? We added a little bit more. This was the second incarnation. We also added the labels and creators. So who created this? A lot of the metadata of these classes, synonyms, namespaces, and all of this. And we used some pre-trained model on PubMed, and we called this OP8bank. And all it does is literally just takes the axioms. It can infer them also. So it adds some inference on these axioms. So it basically computes the transitive closure. And then it adds all the labels and definitions and so on. So we took all of this and we just put it in Word2Vec. That was it. And for this, this is just a benchmark which we use to predict protein-protein interactions based on the functional similarity of proteins. So just Go annotations. And you can see this without a reasoner. So our baseline here, Resnick similarity with best match average. This was more or less the state of the art for this task at the time that we started. This is at the bottom. So you see this Resnick, it's a semantic similarity measure. And Ontologies with cosine similarity and no deductive inference didn't really work so well, didn't beat our baseline. So this is just the axioms. So just the axioms with deductive closure works better than without, but still didn't beat our baseline. Then we had Ontologies, so just the axioms, and we trained a neural network on some of these protein-protein interactions. Basically, we said cosine similarity may not work so well. Maybe there are only some features which correspond to these proteins interacting, and some other functions, they have no relevance to this. So in some sense, you can see this as a trainable or data-driven similarity, or way to compute similarity instead of cosine similarity. And you can see this worked very, very well, with an almost 0.1 improvement over our baseline. And then when we also added the labels and definitions and all the rest to this in OP8, and even with cosine similarity, we did quite well. And then if we also train this, then we would improve over our baseline substantially. I mean, it was a huge improvement over our baseline. So this made me quite happy for a while, because this is something that is applicable to a very broad class of problems in bioinformatics. So whenever you have two entities or some entities which are characterized with ontology classes, and basically every entity is like every variant, every drug, because even with multiple ontologies. So for drugs, you know, where are they metabolized? What are the go functions of their targets? What are their side effects? All of this you can encode in ontologies. So you can embed them using these methods, and you can train a similarity measure. If you have some cases, you're like, okay, these I want, or some, it's not really a similarity measure, it's more like a relatedness measure. But you can train this, and you'll usually see quite a substantial improvement. And there are several reasons. So one is that the complete ontology is part of this embedding. So you have all the axioms in the ontology. So you have a lot of these relations between different classes, which are very indirect, and just through the axioms, you get this. And and you can tune it to your task. So this is a data-driven way in which you can identify these relations. So you can do it for phenotypes, so phenotypic similarity, and we have done a lot of this on phenotypes, so we applied these methods a lot to phenotypes. You can do it for functions, you can do it for anatomical site of expression. We have tried this as well, so where are things expressed? And you can define different types of similarity based on this, depending on how you choose your ontology. So it made me happy for a while, but there is something that is still did not make me very happy. So this is basically, it's still a somewhat stupid approach. Stupid in the sense that there is nothing really that we know about this formal language that we use to express our axioms that we have used to make this work. So this is just based on co-occurrence patterns in description logic axioms treated as language, and surprisingly, or not so surprisingly, but suddenly it works. But it's not really where we would want to be, or at least we should be able to do better if we can actually somehow incorporate some of this semantics and more meaningfully. The semantics of this language, so the meaning, the language that we use to express our ontologies. So we went back to the drawing board and tried something entirely different. So the question is, what do I actually mean when I talk about semantics? So the semantics of this language. So what is that thing? So when we talk about this, then you'll find, if you look at some description logic conferences or OWL conferences, then you see these kind of tables. They give you a syntax, a syntactic construct, and then they define a semantics. And the semantics, it's essentially a sigma algebra. So what this means is there are certain symbols. These are the names of the classes and relations and of the instances. This is our signature sigma. And then we define a relational algebra, which means we have some non-empty set called our universe or our domain of discourse. This is this big delta here. And then we just define what needs to be true. If our axioms are true, how does this reflect the interpretation of our predicates, our relations, our instances? So how does this constrain this interpretation in this sigma algebra? So you can say, for example, if we have this as part of our axiom, so we have this conjunction, then, well, the interpretation of C, and this corresponds to the interpretation of C intersected with the interpretation of D. And the one axiom that I have here is C is a subclass of D. C and D can be complex, so they can have different operators. So it doesn't have to be names, C and D. So they can include intersection or quantifiers and so on. Then it basically says that C, the interpretation of C needs to be a subset of the interpretation of D. And this is a very, very lightweight description logic called EL that I show here. But to say that we want to use the semantics, what we want to do is we want to basically take this syntax and translate it in something like on the right, what is in this semantics part. So this translation, this means preserving the semantics. Well, okay, so how do we do that? And our idea is, you see that in a sigma algebra, which is the foundation of any model, or in the sense of model theory of a description logic theory, or of any kind of logical theory. So our idea was this domain of discourse is not actually, so this universe is not actually constrained. So what if we simply take the Rn itself? So this is the target of our embedding. So the Rn becomes this domain of discourse. And then we just have to make sure that all the other properties are preserved within the Rn. So we take a very specific sigma algebra here. So this is the key idea of this. So what we are trying to do is we have our knowledge base or ontology with a signature sigma. Then we want to find an embedding such that the image of this embedding is the model. So basically, the embedding is the function or the map which maps syntax to semantics. So this is going to be our embedding. And we know that these models exist for OWL2EL or for EL++. This is a core theorem for the logicians among you. This is a very old theorem called the theorem of Löwenheim and Skolem. So it's not so important, but at least the existence of these models is guaranteed. So now the question is, how do we get there? Well, we have two parts. So the first is, our idea was we define these embedding functions, but essentially these embeddings map concepts or classes to points in an n-ball. It's an open n-ball for a technical reason. And the aim is that the extension of a class C corresponds to all the points of the Rn that lie strictly within this n-ball. So the n-ball is defined by a sphere which surrounds it, and anything that properly lies within this sphere is this extension. So this is the set that is the extension of C. And for relations, they are simply a vector such that, so they just need to be pairs of points in the Rn. And here we simply use, it's based on a model called trans E. It basically, X and Y are points in the Rn. So in n-dimensional vector space, then we say that X plus the embedding of this relation needs to be identical to Y. This is the extension or the interpretation of our relation R. So this is the idea of this. So we have an embedding for classes, they are balls, and relations, which are essentially linear, these linear transformations, just moving this ball by a vector. That is going to be the interpretation of a relation. Well, and then we use the axioms in our theory to find these embeddings. And for technical reasons, it suffices to focus on certain normal forms. So I just give one example. So this is a loss, which we simply define for one of these particular forms. So they are finite. There are only 4 of them for this language that we target. So for C, subclass of exists RD. So this is our loss. The crucial part is the red part. And essentially what this does is it shifts this ball corresponding to C by R and forces C plus R, so every point in C shifted by this vector R to lie within D. So D is again represented by an N ball. So C is an N ball, D is an N ball, R is our translation, it's our relation. So if every C needs, so C subclass of exists RD means every C needs to stand in a relation R to some instance of D. Then if we do force this N ball C shifted by R, so every entity in there standing in relation R to some other entity, this needs to lie properly within D, then we have captured exactly this semantics. When we do this, and then there is a margin and some regularization, classical stuff. So we do this for a number of different normal forms. Here is just C subclass of D on the left. So C subclass of D, C needs to lie strictly within D, and so on. So we have some other kind of transformations for the different normal forms. And I'll show you a nice animation. I hope you can see it. So I can show you, this is just an example on the right. It's basically not taken from biomedicine. It's a small knowledge base about the family domain. So what you'll see here is there is father. So this is visualizing this optimization process every 10 epochs. And you can see this red circle here is male, and then there is a father. It's getting very small. It's green here. You can see it shifting around. You can see it shifting around a little bit, but father needs to lie within person and within male. And the blue circle is parent. Yes, so a father is a male person and parent in here, and it will remain in this intersection, and this all terminates when male is entirely within person here. So this is now, it's shifting and it's moving male into person. And in the end, this is just in 2D space. Normally we would do it in some higher dimension, but just easier to visualize. And the interesting thing is that we also have some formal guarantees about this process. So we know that if we can reduce the loss to 0, then this knowledge base has a model. So this is called soundness, and it's 1/2 of a rather strong aim. So the inverse of this is called correctness. So if T has a model, then we can also generate it using this approach. Correctness does not hold. Completeness, I'm sorry, completeness does not hold. In this case, we have a number of counterexamples and some ideas to fix it. So now I can show you, this is a slightly different test. We compared it in a different setting on the same PPI benchmark that we had before. And you can see EL embeddings. Again, it performs much better than Resnick similarity, some other similarities, some other embeddings, including trans-E, so just graph-based embeddings. And at the bottom, you see something that is called ELBA. I'm not going to go into detail. You can look it up in the archive if you want to. It's essentially the same thing that I just described. just with boxes instead of balls. So no balls, just boxes. So axis parallel rectangles. And the crucial advantage of using boxes over balls is that the intersection of two boxes is again a box. So of two axis parallel boxes is again a box, while the intersection of two balls is not a ball. So it becomes a lens. And if you want to model intersection, then boxes are a lot better, and there are some intersections in Go. It works better for them. Okay. I'm nearing the end, but I want to show you something very interesting that we can do with this EL embeddings that we cannot do with any of the other methods. And this is zero-shot predictions. So take the case where you have an ontology and you want to predict whether some entity, based on any features that you might have, whether some entity belongs to this class or is related to this class or not. In our case, we wanted to predict protein functions, but we wanted to predict it for functions for which we simply have no protein. So there are functions in Go, and we have never seen a protein with this function. And the question is, can we maybe use this method, this EL embedding approach, in order to predict these functions? And we call this zero-shot prediction. We want to predict instances of C, or in our case, it's not instances because proteins are not the instances of the Go classes, but there are annotations to these Go classes, or they stand in some has function relation. But fine. The assumption that we make is that C, this class that we want to predict, is used in some kind of axioms. For example, C subclass of exists RD. And this is the case. Or C is the intersection of A and B. So, or in some other more complex axioms. So if we have this, then the question is, within this embedding space, are we able to still predict that something is related to C, even if we have never done any training on this? So this is now not a very clear figure. So this is the model that we have built, but essentially you see this EL embedding model here. HF is has function, so it has function for a protein. So this is this embedding model. It's this EL embedding model, and there are a couple of axioms here. And on the left is a protein, and we have the amino acid sequence of this protein. We can extract some features. Many ways to extract features. I mean, there are 500 methods to extract features from a protein sequence. Let's assume you do something simple, like you just represent it by their interpro classes. Or so you run interpro scan on this protein, you get a number of interpro annotations for this protein sequence. So, well, how do you use these two sides to predict it? Well, so here we have, for example, interpro or some features of our protein, and we simply use a multi-layer perceptron. Very simple two-layer network, I think. A very simple multi-layer perceptron here that has as an output a representation of this protein, or any of the features that we used for this protein, of the same dimension as a point in our embedding space. And the optimization objective is that we can infer functions within this embedding space based on the embedding that this multi-layer perceptron, this very simple neural network, created. So this on the left-hand side, this small neural network here, simple multi-layer perceptron, is only there to project this protein, represented however you like it to be represented, into the same space as our EL embedding space, in such a way that we can infer these functions. So we have training data for some proteins. So here we would infer functions based on exactly these types of axioms that we have formulated. So using this transformation by R, so this is our has function relation here, so has function sum C. So this is one training axiom. Well, and then we can infer this for subclasses of this of C, for example. So D is a subclass of C. We can infer functions of D, even if we have not seen, and they may be otherwise constrained. And you can do this, and it works if you pre-train your embedding model based on the axioms, and then separately just do this projection. But it works better if you jointly optimize this. And you can see this in our ISMB paper this year, DeepGo 0. It's also on bioRxiv, so you can have a look at all the details. This is mainly the work by Maksat. Okay. We can test this, so you can see this here. We just compare it using just a standard prediction model for Go functions. And here you can see on the x-axis, you have the number of training instances we have for a Go class. So this is based on Go class. So this is the average AOC by Go class, starting with only 1 to 5 training instances. We cannot compare it with an MLP with 0. So the 0-shot prediction just doesn't work for multilayer perceptron, because if we have no training instances, it's not going to predict anything for this class. So we start with 1. You can see there's some difference, and this difference gets smaller and smaller. And at some point it disappears. So this difference between DeepGo 0 and just a multilayer perceptron. So at some point, if you have enough training data, just a multilayer perceptron will be equally good as this DeepGo 0. But especially if you have very little training data or no training data, this is what you can see on the right for just a selected set of classes. You have no training data, then this is then you can still predict, in some cases extremely accurately. Of course, not in all cases, but in some cases very accurately, just based on the axioms and training for some other classes. We also built a library for many of these methods, so a software library. So it's a high-performance library. It includes reasoning and machine learning. So it has this bridge to Java and the OWL API using JPipe. It's quite difficult. It's a Python library. So it's entirely in Python, and it has this wrapper around the OWL API. So you can use the full OWL API from within Python using this JPipe, which is quite efficient, and it's quite performant. So it's quite fast. You can access this whole, you can access all the reasoners in the OWL API and so on. But we implemented most of the algorithms and many more. So OWL to Vex star, a number of other algorithms, not just ours, from other groups in here. And it's free software. It's in a beta version still. So this is my student Fernando is working on this very actively, and he basically updates it every day. But you can test it, and he's very happy if you're interested in these methods. He's always very happy for feedback, and he's also very happy to see that people actually use what he's doing and find it useful. So if you work on these methods, please have a look at this library. And even if you don't like it, you can tell Fernando what you don't like, and he will fix it for you, I'm pretty sure. Okay, so there are a number of different questions. I talked about the n-balls. Fine, we can do this. There's still some missing completeness, and some of these models may be degenerate. Our relation model is rather simple. This is easy to fix, but it doesn't necessarily improve the performance to go to a more sophisticated or better relation model instead of trans-E, just because they always get more complex. They're harder to optimize and easier to overfit. And we want to do this for ALC or more expressive logics as well. So the next steps is a lot more theory for this, because this is still missing. And this is something, the key advantage that I have mentioned in the beginning of symbolic methods is that we have this whole theory. So we have all this theory, and we have these formal guarantees. They are incredibly useful, because in the moment, we basically train some deep learning model and hope for the best. But having some formal guarantee of what is and is not doable with our model is something that is incredibly useful for analysis of these models, for robustness, and for tolerance to biases and removing biases. can simply constrain our model if we are guaranteed that it will behave that way to not be sensitive to certain types of biases that we know of course. So for this, we work on a number of different approaches. So we work on fuzzy logic with differentiable t-norms. So this is one of our big research themes at the moment. We also work on a second one, on a second idea, which is based on category theory, and it's the relations to type theory and proof theory. This is very theoretical, but it may be comprehensive in that it can encapsulate all the different methods that I have mentioned so far. But the aim is essentially to have neural networks that can not only learn to recognize patterns, but also to reason. And we want to have this MAUL as basically as the go-to place for people who are working on these kind of neurosymbolic methods with ontologies, with OWL ontologies or semantic web ontologies in particular. So this is our MAUL library. And just in summary, how this fits into the bigger picture that I started with also in the beginning. When you go back to Feigenbaum, this is a quote from a very, very early ICHKAI conference, where Feigenbaum, he started with his paper there. He started this surge in expert systems in medicine and everywhere. Where he gave, this is just a quote from his paper, where he says that the domain-specific knowledge plays a critical role in organizing and constraining search. The theme is that in the knowledge is the power. And he intended this for things like tree search or graph search, where you had to explore huge search spaces as well. But now our search has changed. So we don't care so much about tree search anymore. These problems have been solved. We do continuous search. So optimization, gradient descent, is a search for an optimum, for a minimum or a maximum of a function. So it is also a kind of search. And for this type of search, we now need to build methods again that can utilize the knowledge or domain-specific knowledge in order to constrain it. Not only to improve computational performance, but also to make these models much more robust. And this is where this theme fits, or where these methods fit into the central area of AI research today, where we add constraints, we can use them to remove biases, and we can hopefully get more robust methods. So that is it. I'd like to thank my group at KAUST. So this is a 2019 picture, pre-Corona times. We didn't have so many opportunities for pictures, and thank you very much for your attention. And hope we have some nice discussion now. I hope I didn't go too much over time.
Thank you so much, Robert. This was great, absolutely great talk. Thank you. So let me see. I have a few questions. Feel free, everyone, to raise your hands. Okay, Jacqueline, go ahead. Take my next spot.
Oh, thank you, Raphael.
Sure.
So this was really a great talk. Thank you so much. It was so helpful to kind of understand the algorithms and the math that go into the back end of these ontologies. And so my question is about like things that we don't yet know. So when we're talking about the traditional way that the traditional methods and using things that are known, like, like the colors or the kinds of trees, and using those to kind of build models, like how does that translate into creating these models for algorithms that are unknown? For example, protein-protein interactions aren't always, we don't know for sure what binds with what, or I guess, does that make sense?
Yeah. It's a good question, and you of course identify some quite some limit of what I have presented. So of course we have. So let me just go back here, right? So we have these methods, and they essentially semantic similarity, and we still need to formulate a hypothesis, and the hypothesis is something that is from here. So it's basically, if two proteins are functionally similar, then they are more likely to interact.
Mm-hmm.
So this is the biological hypothesis. And we can evaluate this based on what we know about protein-protein interactions. For yeast, they might almost be complete, which is why we test this mostly on yeast.
I see. Mm-hmm.
For human, not complete, but we're probably quite good. For all other organisms, we know very little. Now, these methods, of course, they would work if they would work. So you can do this for protein-protein interactions. This would work if we know the functions very well. But usually, if we know the functions, we also know the interactions.
Right.
So if we know the functions very well. So it's not a very useful test. So this is not a very useful test, but it's a very useful benchmark to use. More useful, and I realize I have not shown you many actually useful methods, especially for your research, but more useful questions are questions where you use this to compare, for example, patients with based on their phenotypes, or mouse models, so knockout mice with a patient. So you can screen mouse model databases based on patient phenotypes in order to hypothesize which gene this patient may have a loss of function variant in. Or you can use this to screen OMIM for it, or ClinVar. So the how to use them is a somewhat different question. So you would have to be very careful in how you formulate the hypothesis and how you test it. So this is quite right. And yes, I did not show this, but you can formulate all of these. There are papers not by us, but by several other people who have explored these questions or larger questions using either semantic similarity or these embeddings. And if you like, I can send you some papers for all of these questions to see how they have done it. So I can, yes. Does this answer your question?
Yes, thank you. Thank you so much. That would be great.
I'll jump in with perhaps a short question, but here I noticed your hand up, Tyrone. I'll get back to you, but just out of curiosity, Robert. So here you kind of focus a lot on, we've got this symbolic representation of our entities already. What happens in a scenario? I'm wondering whether this kind of fits in. What happens when we don't already have a symbol for our labels, or perhaps we have some characteristics, we know some features of those labels. Let's say we're looking at the UK Biobank and we have like 10,000 observations or so, and we want to infer a phenotype out of that. So can you say a little bit about how can we project unknown things into symbols and have some kind of, perhaps, I mean, ideally, can we project them already in a hierarchy at least? So along there is a hierarchy. Can we do that? Can we do something a little bit more complex, part ofs or things like that? What can we learn out of these unknown symbols?
Yes, this is a great question. So maybe you remember this very nice paper by Trey Idegger on data-driven generation of gene ontologies. I think it was in Nature Biotechnology some time ago. It was essentially based on data-driven clustering of similarities based on some interaction networks, but it was basically some data-driven approach to identify clusters. And some of these clusters would directly map to cell components in Go. And some of these clusters had no classes in Go, so they were clusters they would clearly separate, but they do not have a name. And for this, Trey Idegger had an algorithm to give them a name and also to generate a hierarchy from them. And of course, you can use some form of hierarchical clustering and use it together with Go. In general, this whole question is the question of inductive logic programming and concept invention. So how to generate, when to generate a new concept and how to generate axioms. So how to relate them to symbolic knowledge. And it's part it's essentially part of this extraction process. I didn't talk about this. I'm sorry.
It's okay.
But so there are many different methods on this that are coming up now. So there are a lot of traditional methods for inductive logic programming, but you can take, for example, Trey Eidegger's method on this data-driven, I forgot the name, it was the name, I forgot, Clico or something was the name of the algorithm, as a way to generate hypotheses about symbols which should exist and how they should relate to existing classes in the Go. And you can then use, and he didn't do that, but you can then use in this framework, you can use this reasoning mechanism on the symbol system to test whether the axiom that you have inferred is consistent with the rest of Go. So you can also now, there are also methods based on reinforcement learning to do that. So you can use reinforcement learning to do something quite similar, and a couple of other methods for this in the context of inductive logic programming.
I see. That's great.
There will be some of these methods part of MAUL. So this is our plan. They will be part of our library because, and some of them already are, but they do not currently include concept invention. So concept invention is something that we don't cover yet, but you can currently add new axioms and test them for consistency based on how you recognize patterns here.
That's great. I will definitely look into MAUL and experiment with it, provide some feedback. Thanks, Robert. Tyrone, you still there?
Yeah, should be a very short question. Might be because I'm very naive to some of the semantics that you've shown us, Dr. Hordendorf. But one thing, questions I had was exactly whenever you're running these embeddings or axioms, exactly how strict are they in the sense of the model right there? Is there a parameter which to tune how are these hard or soft these axioms are with regards to your ontology?
Very good question. The answer is there is no such parameter, no. You can, when you have finished them, you essentially get a remaining loss at some point, which will not improve much at some point any longer. And you can assign a weight to types of axioms or also individual axioms. It is useful when the types of axioms are heavily imbalanced, but there is no parameter on how strictly they are enforced. So they are all quite soft constraints which are encoded in a loss function.
Interesting, thanks.
Maybe you have ideas on how to make this more strict. I mean, I would be happy to hear them.
Laha, did you have a question?
Yeah, I have a quick question. Maybe it's a very general question. So instead of try to turn those to like similar to word embedding, if I understand it correctly. So the knowledge graph seems like a graph model. So why you don't think about use like a graphical model, like a graphical network, instead of we have to transfer it into like a word, use those similar to natural language process.
Yes. Yes. You can use MAUL and you can use different graph models, including graph neural networks and other knowledge graph embedding methods. Initially, so 2017, they didn't exist and we didn't come up with the idea, unfortunately. So we used random walks at the time. And they still have some advantages. So these word-based models, they are very simple. They scale very well. And for some cases, they seem to also generate much better embeddings in some cases. And why, I'm not exactly sure. But we tested a number of different approaches, and things like node-to-vec seem to work very well compared to the newest graph neural networks, and that also generate node embeddings. And why this is the case, I cannot really tell you. I do not know. But in principle, it's I try to keep this very flexible. So here there's some graph embedding, and random walks is just an example. So you can, it's a parameter how you embed this graph in there, or the nodes in this graph. And there are many alternatives. You're absolutely right.
Okay, thank you.
Great, thank you so much. I think that I don't see any more hands up. I want to be respectful of folks' time. So I think with that, I'll just close off, and thank you so very much, Robert. This was absolutely fantastic. What a great talk. I'm sure there'll be some follow-ups. I think that perhaps we have a bit more talking to do around the phenotype space, because that's what we're sort of trying to do. But other than that, I think, thank you very much. Thanks everyone for being here. And again, thanks, Robert.
Thank you very much, and have a great day.
Thank you, you too. Bye,
Thanks,
everyone.
bye.
Bye.